Swayam Prabha. Digital India. Educated India.
All right, so let's go back to our, so now again I'm going to denote the desired vertex by k, just to recall that we are trying to see what are the circumstances under which we can make a co-planned winner an actual winner of the tournament, because it seems like a high out degree is a good place to start. So we are taking the vertex with the maximum out degree, and so if you focus your attention on the king, she naturally breaks up the rest of the tournament, the rest of the teams into two sets. So there are the players that she beats and then the players that she's beaten by, right? And in the first, so what we really want to do is come up with a sequence of matchings, right? Where k turns out to be, k emerges as a source vertex in every stage, right? That's the goal. So at least to begin with, I know that in the first matching, I must match k to some player out here, right? And how do I want to match the rest? I mean, at least intuitively, let's say that, so I'm going to propose two matchings. Maybe you can tell me which one you would prefer. Okay. So let's say that there are six players remaining. So it's a total of 8 players. So k got matched to some player a that she is defeating. And here is a matching that's just matching, it's a matching going across from n plus to n minus. So that's the blue matching. And I'm going to also propose an orange matching, which picks the same edge as the blue matching here. So I don't know if it's useful to give these players names. So let's say X, Y, Z on this side, P, Q, R on this side. So the blue matching matches X to P, Y to Q, and Z to R. While the orange matching matches, the orange matching matches X to Y, P to Q, and again Z to R. So these two matchings really represent, in some sense, represent two seedings. Which one would you prefer? Which are the set of playoffs that seem to make more sense from the point of view of k? Is it the orange matching or is it the blue matching? How many of you think it should be the blue matching that we pick? Okay, so a couple of you. How many of you are in favor of the orange matching? Okay, anyone prefers the orange matching? Okay. Yeah, so right now I'm assuming that it's K, A, X, Y, Z and P, Q, R. Let's just say these are the only 6 players in the mix. In that case, again, I'm not going to try and prove anything formal here, but intuitively, which of these two matchings seem to be better for the player K? So if we did go with the blue matching, then who are the players who move on to the next round? So K for sure, because K defeats A, and then X, Y, and Z, right? And X, Y, and Z are all players who are defeated by K, right? And so after this, you can be stress-free, because no matter what happens, K is going to win. Like K becomes a Condorcet winner in that sub-tournament, right? On the other hand, if you pick the orange matching, I'm not saying that all is lost, but players who defeat K continue to survive in the mix, and you have to worry about ensuring that you get rid of them before the final playoff, right? So you will still have some stress in the second phase. You'll have to be careful about the next matching that you pick. I'm not saying it cannot be done, but if you had a choice, you might as well go with the blue matching. Like if a matching of this kind exists, it may not. So in particular, the arrows that go across from the green set to the red set may not be pointing so nicely in your favor, right? So we want to see what is the best that we can do. But would it be fair to say that it makes sense to, first of all, it makes sense to match K to a player in the green set, because if you don't do that, then K is already out of the game. So that is necessary, right? Among the remaining seedings, it makes sense to say that because of the example that we just discussed, it makes sense to say that we want to match off as many people from the green set to the red set as possible, provided, match off as many of them as is possible, as long as the arrows are pointing from the green set to the red set, okay? This sort of thing doesn't help you much because it actually knocks out a player that is good for you, okay, and pushes up a player that is dangerous for you, okay? So matchings going this way are not very helpful. Edges going that way are not very helpful, but try to max out on the edges going from the green set to the red set, because that maximizes the number of survivors who are favorable for the player K. These are players that K is comfortable defeating. So the more that proliferates, the better off I am. So I'm trying to see how many can I push out from the red set, as many as possible, right? That's the goal. So here's a proposal. Let's match K to some player in the green set, and let's maximize the matching. Let's compute a maximal matching from the green set to the red set, okay? And we may still be left over with some players on both sides. So by the way, we have an even number of players altogether. And after you forget about these two, you still have an even number of players, but they may be split as odd, odd, or even odd. Even. Okay. And just to say the number of remaining players after you have done the blue matching, you may be left with either an even number of players on both sides, in which case we just try to match them amongst themselves, right? So matching them, again, I'm playing on intuition here, but it seems to make sense to match AB between them in this example. So I've already used small a here, so let me say B and C. Between B and C, I'm better off matching B to C irrespective of the direction of the arrow, compared to matching B and C to one of these remaining players here. So let's call these W, X, Y, Z. Why would I not want to match B and C to the other side? So if I didn't match B and C amongst themselves, then since I know that I have to come up with a perfect matching on this whole set, if I didn't match B and C amongst themselves, then both of them will be matched to players on the other side. And between B and C and any of these other players, who is going to win? Yeah, given that the blue matching is a maximal matching that was going from the green set to the red set, a maximal matching is a matching that cannot be expanded upon anymore, which is to say that there are no more edges left which are going from the green set to the red set. Yeah, because if there was, then you could have extended the blue matching, contradicting its maximality. So all the remaining edges are pointing in a direction that is not good for you. So this is the situation for every edge between W, X, Y, Z and B and C. So if you were to match B and C to the outside world, then you would lose both of them, and you would actually be pushing two of the red players, two of the dangerous players into the next round, Versus if you match B and C amongst themselves, you do lose one of them, you can't help it, but you at least lose only one, right? And by pairing of W, X, Y, Z amongst themselves, you get rid of at least two of them. But K, right, but K has been matched to A. So, so I'm talking about the parities of the remaining players. So in fact, I'm talking about the parity of the sets that are left behind, the players that are left behind after after these folks have been matched off. So the red edge and the blue edges, let's pick them. The blue edges are, let's say, the maximum number of people that I can match from green to red. And Ka again is something that I have to do. I mean, I have to match K to somebody inside, right? Now let's look at how many players are left. So those are the black star vertices, and that composition could either be, so we started with an even number of players, and we have gotten rid of players across a matching. So we have removed an even number of players, right? So K and A and both endpoints of the blue edges. So we're still left with an even number of players who could be split as odd or even. And if the split is odd, then you don't really have a choice. You have to suffer a red edge. Okay. Yeah. So that's something that we will pick if required, right? Because notice that there's no question of optimizing the green-red split. That is just by definition. I mean, that is just reflective of the quality of the player K. So that's something given to you by the tournament. Okay. So this is pretty much the algorithm that we are going to try and formalize now. So I've just pulled this out from the handbook. So let's just sanity check. I mean, given the discussion, it should now be reasonably straightforward to go through this procedure. We'll still have to argue that the procedure makes sense, and we'll come back to that. But this is the formal description of the algorithm is recursive, which is to say that, so we are trying to build, so the notation that they use, so let me just flag this for you. Okay, so that's the wrong thing to use, sorry. So the notation they use is that you want to output a collection of matchings, and every matching is tagged with the round number of that matching. So I mean, you can, by looking at the size of the matching, you know which round it represents, but just to be clear, this is the log mth round. So log m for us is K. So in the last round, you just have one matching edge, right? And here again, what you have is, again a matching and a round number along with the remaining matchings which are being delegated to recursion. Okay, so we'll come back to this in a second, but let's just go through the base case, which is easy, which is to say that if you're just left with two players and one of them is the player that we are interested in, which is K, then we just return K comma A. And as long as K is a king, so this is what we would like to be able to argue, that we maintain the property that K is a king as we go along, that when people get knocked out by our matchings, we don't lose too many of the green vertices and K can retain its king status. That's what we want to be able to show. Okay. So that's what we will be able to show is something slightly different, because it turns out that working with kings is not enough. So go back to the question of, you know, can you always make a king win, or can you come up with an example where it's not possible? Okay, but essentially this is the split that we were discussing. So A prime is the out neighbor. So A prime is the set of players that are defeated by K, and B prime is the set of dangerous players for K. And in the first step, we arbitrarily match K to some player that she defeats. Okay, that's the first red edge that we saw on the previous slide. And then we are going to construct these 3 matchings to be able to perfectly match everyone else. So the first one is a maximal matching from n minus a to b dash. So that's the blue matching that we saw on the previous slide. Yeah. So you match as many as you can, and then you match the rest within themselves. And if you're still left with somebody, and that will happen only if there is an odd, if the split is odd and odd, then you're stuck with somebody one on each side, and if that happens, then as we said, you suffer this red edge. All right. So that's the matching that we are going to return for the current stage, and recursively we are going to output the matching that is obtained by focusing on the sources of the current matching, because you propose this matching, who is going into the next round? The set of players who are the sources of this matching. So on that you recurse, you go as you did in the current round, and this will help you build up a full collection of matchings for the entire tournament, right? Yeah. Right. Yeah, that's a good point, and I think that's an optimization that we can do, because if this A was somebody who had an out neighbor to the other side, you might as well leave it alone and pick a different A. It turns out that for, I think, the specific statement that we are going to prove, it will not be required, but you might as well do it. It will not hurt. Yeah. What we're saying is that even if you pick it arbitrarily, it's still going to be enough, right? So I just want to make sure that the process is clear. Okay, we haven't made any claims about any concept of correctness so far, but at least how are we determining the seeding? Hopefully that is clear, right? Yeah. So seeding would be the labeling of the leaves of the tree. So it's this thing here. We are trying to figure out how do we set up the playoffs at the bottom round, right? And in fact, what we have done is in the first step, we have only given you the let's see. So we have only given you the pink matching, okay? That's what we did in here. We said we'll look at the king, we'll look at all the remaining players, and we'll match the king arbitrarily to somebody that she defeats. And then among the remaining players, we will greedily match as many as possible from green to red, okay? And the remaining we will match amongst themselves. And if the parity doesn't work out, then we will also take one edge from red to green, right? So this is one matching, but notice that this is not the complete seeding, because if you just give me one matching, then you have told me that these are the pairs, but you haven't told me in what order the pairs are sitting on the leaves. So I know that this is the collection of pairs that must go and sit on the leaves, but you haven't told me what's going to happen in the next stage, right? So this is a collection of playoffs, but you haven't told me the winner of this playoff should face the winner of which other playoff. So that will come from the second matching, which is a matching on the sources of the first one, which is a matching on the winners of the first stage of playoffs. So that's why this is an incomplete description of a seeding. It's like the labeling is beginning to emerge. So you have a fuzzy notion so far. You know that these are going to be the pairwise playoffs, but to organize them further, you need the remaining matchings. Yeah. All right. So and the remaining matchings will be determined recursively. So you take the sources and then you run this process again. You take the sources and you focus on the sub tournament which is given by the sources of this matching, and you do this again. And there may be the burden of proof is now showing that you can always, like, you never empty out the green set, right? Because if you are in a situation where, let's say, there are no blue edges, okay, and then possibly you just have one vertex left in both the sets and you're forced to pick the matching in the other direction, that's a bad situation for you. So you want to understand when can you avoid that situation, right? So it's not clear that this will simply go through, but it is a legitimate process for picking up a seeding, and you want to show that Well, I mean, ideally you may want to show something like if K is a king, then she will survive in every round, and she will always, the green set will never run out, and you will always be able to pick that first edge, which is KA, which is so necessary for the king surviving all the way till the end. However, that's not exactly the statement that we will show, because it's not clear that that statement is even true. But what we are going to say is that if we can empower the king a little bit more with some additional properties, then this process will always go through. Okay. So there is a notion that we define at this point, which is the notion of a super king. So let me just write this down. The super king is a vertex which is more powerful than a king, as you can imagine. So it's still a vertex with maximum out degree. But every vertex that it doesn't beat is beaten by at least log m vertices that it does beat. Okay. So all these logs are to the base 2. Okay. So by log m now we mean k. So I don't know if this is visible, but basically for every vertex, so for every vertex that V does not beat, such vertices get beaten by a lot of vertices that are beaten by V. Okay. It's a bit of a definition to keep track of, but hopefully the intuition is clear. What we are trying to capture is this idea that we'll never run out of constructing our blue matchings, right? So what we want to say is that that's a rich set. So so we'll always have plenty of opportunity to be beating out the red guys in the picture that we just created. Yeah, that is the idea with the definition of a super king. So in fact, just to be precise, this is all that we need for a node to be a super king. So we don't explicitly require maximum out degree. All we are saying is that for every vertex that you're not beating, there are plenty of vertices that you beat that they beat, okay, that they're beaten by. And I think it's a good exercise to check that super kings may not always exist, just like Condorcet winners may not exist, super kings may not exist. But notice that a super king is a weaker notion than a Condorcet winner. You're not demanding that you defeat everyone. You may be defeated by some people, but for everyone that you're defeating, there are a lot of players that you defeat who kind of stand guard between you and that vertex that is defeating you. So it's a notion that is stronger than the notion of a king, but weaker than the notion of a Condorcet winner. It's something in between, and they may not always exist, but we will show that the algorithm that we were proposing implicitly proves that if a super king exists, then we can always make her win. Okay, we can always make her win. So there's always a seeding that makes a super king win, and that seeding is the one that is given by our algorithm. So in other words, if K is a super king, then our seeding process never gets stuck. That's what we want to say. So in particular, what happens when you move from one round to the next is that your focus shifts from the full graph to the sources, right? So these are the players that move to the next round, correct? So what you want to show is the following. You want to show that if K was a super king in the current scenario, then K continues to be a super king in the new scenario, okay? And if you can show that, then you can use that lemma to formalize an inductive proof for why the algorithm will go through. Because you can say that suppose on every tournament that has K players, if there is a super king, then you can make her win. Then for every tournament on 2K players, if there is a super king, you can make her win, because you start out with the tournament on 2K players and propose this matching for the first round, right? And then you know, because of the lemma that we are going to prove, you know that the people who advance to the next round, which are the sources of this matching, on that sub-tournament K continues to be a super king, and at that point you can invoke the induction hypothesis to complete the seeding. Okay, so the induction hypothesis will essentially validate the output of this recursive call. Okay, so we're saying that on all smaller sub-tournaments, things work out nicely. That's the inductive hypothesis. But to be able to apply the inductive hypothesis, my burden of proof is to show that the special vertex that I'm looking at continues to be a super king. Because the inductive hypothesis says that on all tournaments on K players, we can make a super king win. So when I'm proposing this seeding here, when I'm proposing this matching here, I want to make sure that in the sources of this matching, among the sources, K continues to be a super king. I have to demonstrate that. Once we demonstrate that, then we are done, because then the inductive hypothesis applies and the rest of the algorithm works correctly. The recursive call correctly outputs seeding on the smaller subtournament. Is that clear? That's the framework of the proof. Yeah. Okay. So really, we have to show that among the sources, K continues to be a super king. So we don't have to say anything about the vertices in A prime, because they are all out neighbors of K. Remember that the definition of a super king is that if you are defeating K, then you must be defeated by a large number of people who are defeated by K. That was the definition of a super king. So let me just recollect it here quickly. So for every B that is not in the out neighborhood of K, right? Yeah. So let's focus on the players who are in B prime, who survive in the next round, because these are the in neighbors of K, and that's where we have a burden of proof. So if you are an in neighbor, I want to say that there are lots of out neighbors who are beating you. So if you are an in neighbor of K who made it to the next round, why was that? It was because this maximal matching couldn't catch hold of you, right? Yes? Okay. Now, what can we say about the edges that are going? What can we say about the edges that are going from the sources here to the sources here? Because those are really the edges that will determine whether we have made it, whether we can find. I need to find enough players among the sources of A prime who are beating a typical vertex here. So let me focus on a vertex B here. I want to show that it has a lot of in neighbors in the set of sources of A prime. Right? That's the goal. So can you think about where these neighbors will come from? It'll come from the, so it'll come from the endpoints of M dash. And why would they be so? So this is your claim that the sources of M dash, that matching, would be in neighbors of the vertex P. Okay, why would that be the case? Right, 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 right. Right, excellent. So we know that K is a super king in the current graph, right? So we have to exploit the fact that K is a super king in the current graph, which means that this vertex B has at least log M players who are defeating it in the current graph. Yes, and one of those players could potentially be A. That's the only challenge. But even leaving A aside, you know that there are at least log M minus 1 players, okay, who are defeating B, and each of those players who are defeating B must have been caught hold of by the matching M dash, right? Because the matching M dash did not catch hold of even one of these guys sitting outside, then, well, that's somebody that's defeating B, so why didn't we pick it in our matching M dash? So remember that M dash was a maximal matching, right? So this edge would have joined that matching. So in fact, B is defeating everybody that is not a source in M dash, okay? And since K was a super king, B must have had at least log M guys whom he is defeated by among the sources of M dash. So hopefully that is clear. And log M minus 1 is still okay, because that is essentially log of M by 2, and M by 2 is the number of players in the smaller subtournament. So we have moved into the sources of the matching that we have proposed. That's a subtournament on M by 2 players, right? So having at least log M minus 1 players in the out neighborhood of K who defeat B is good enough, because log M minus 1 is essentially log of M by 2. Okay, so that shows that B is indeed defeated by a lot of out neighbors of K, even in the smaller subtournament. So K continues to retain its super king status in the subtournament, which means that at this point we can in fact invoke the inductive hypothesis. Yeah, so is this argument reasonable? It's clear? Yeah. So super kings may not always exist, but if they do, you can always make them win. And this is a notion that's weaker than the notion of a Condorcet winner. So we made some progress beyond what was trivially true. All right, so this is a nice sort of a greedy algorithm, and notice that we didn't really need to be, it works even with just maximal matchings and an arbitrary choice of A. So we didn't even have to optimize A, we didn't even have to pick a maximum sized matching, even a maximal matching was enough. Although if you were implementing this, you may want to make those optimizations to make things even better, but this will still work. All right, so I think this is a good time to wrap up this discussion, and when we come back, Sushmita will tell you more about the tournament fixing problem on slightly more general tournaments, right? So as we said, what makes tournaments interesting is cycles, and we will dig much deeper into that comment when we return. So at this point, let's break for coffee. Thanks.